Hello everyone and welcome to this explainer. Today we are going to be looking under the hood of something absolutely incredibly powerful, the complex mechanics of SMIDIC Pcs7, specifically focusing on CFC testing and execution. Now, if you work in industrial automation, you know that the surface interface, well, that's really only half the story. So today we're going way past the dashboard and we're getting our hands dirty to see the core engine mechanics that actually drive the logic.
Okay, let's dive into this. Here's our roadmap for the explainer. We will start with live system testing modes, then drop down into organization blocks and priorities, look at optimizing run sequences, cover managing runtime groups, and finally, we'll wrap up with essential execution checkpoints.
Section 1. Live System Testing Modes, the Dashboard.
Observing a live system requires making a truly critical choice right out of the gate. You've basically got two options. First, there's process mode. This is your safer, everyday mode for production environments, simply because the communication load for online dynamization is strictly limited. If you want to monitor something here, you have to explicitly enable it. Then you have laboratory mode. This is basically like taking the restrictor plates completely off the engine. It's optimized for high bandwidth testing, so all registered inputs and outputs are displayed immediately. But listen, there's a massive warning attached to this. Laboratory mode creates a considerable, unlimited communication load with a minimum update cycle of just 1 second. It's high stakes. You literally only use this when you absolutely need maximum data throughput in a safe offline testing environment.
Once you're actually in test mode, the level of granular control you get is pretty amazing. Engineers can monitor and explicitly force individual IOs with pinpoint precision. Hovering over a pin gives you this handy little tooltip fallback that displays the current value. You can also explicitly turn on the For Test property to monitor specific data. But, and you'll want to pay close attention to this, you also have the ability to force values. Changing values at non-switched inputs immediately influences productive operation. You are injecting live data directly into the system's veins. It's a fantastic troubleshooting tool for sure, but it requires the utmost respect because your changes are happening in real time right on the plant floor. Now, what's really interesting about analyzing all these live process values is that we essentially have two distinct lenses to view them through. The dynamic tabular display is absolutely perfect for when you need to see a massive amount of data all at once. Think temperatures, pressures, blow rates across different charts simultaneously. You just drag and drop what you want right into the grid. On the flip side, we have the graphical trend display. This is for when you need context over time. You are plotting those values on a visual curve, though keep in mind you are limited to a maximum of 12 channels per display. Oh, and a quick pro tip. That trend recording doesn't just start automatically. You have to explicitly hit record when you enter test mode to actually start visualizing that time range data.
All right, Section 2, Organization Blocks and Priorities, the engine core. Let's really lift the hood now. To understand the underlying architecture here, you have to understand its primary component, the organization block, or OB. By definition, an OB is the exact exclusive interface between the CPU operating system and your programmed user logic. This is a fundamental, unbreakable rule of SMIDIC Pcs7. You could build the most elegant, brilliant logic block in the entire world, but if you forget to assign it to an organization block, it's just going to sit there doing nothing. It completely relies on a start event from the OS to trigger. Without an OB assignment, your logic block will never execute, period.
But here's the catch. Not all OBs are created equal. They operate on a really strict hierarchy. I kind of like to think of this like a VIP club. Down at layer 4, the lowest priority, you have OB1, the free cycle. It only runs if absolutely nothing else is happening. Think of it as the general admission line. But as we move up to layer 3, we hit medium priority. These are your cyclic interrupts, basically forming the heartbeat of the system. Move up to layer 2, high priority, and you've got hardware interrupts and redundancy errors. And finally, layer 1 at the very top, startup and synchronous errors. These high priority interrupts are the ultimate VIPs. They completely bypass the velvet rope and will immediately pause any lower level task just to execute their critical code. We see this priority system in action perfectly during a system startup. At exactly 0 seconds, the CPU moves from stop to run. Instantly, our VIP layer 1 steps right in. OB100 executes to process special startup code before anything else is allowed to happen. Only after that completes, moving further down the timeline, does the normal cyclic program execution actually begin in OBs 32 through 38. And hey, speaking of startups, I really have to emphasize a critical warning here. You generally want to use a warm restart, which preserves your data blocks. A cold restart is incredibly dangerous. If you execute a cold restart, all your vital process data is permanently destroyed and reinitialized, so always know exactly which startup you are initiating. Moving on to Section 3, Optimizing Run Sequences, Tuning the Timing. So, picture this. You're looking at your live system and you realize, wait a minute, my system signal is arriving 4 full cycles late. Your physical hardware triggered on time, but the output took 4 entire CPU heartbeats to calculate. What went wrong? Well, the answer usually lies in multi-cycle dead times caused by an unfavorable configuration. And this brilliantly illustrates the why behind that delay. When you have an unfavorable configuration, you'll often see these little black diagnostic symbols pop up. That is the system waving a giant red flag, warning you that an input is being processed before the output connected to it is actually ready. It's basically passing the baton backwards, meaning the system has to wait for the next full cycle to carry that data forward. 4 blocks, passing backward, takes 4 whole cycles. But by simply optimizing the sequence so the signal processes correctly from left to right, sequentially from input to output, all those diagnostic black symbols just disappear. The entire result is calculated super efficiently within exactly 1 CPU cycle. So how do we actually fix this in practice? Well, you've got 3 distinct options for optimization. Step 1 is manual configuration. You literally just click and drag the blocks in the runtime editor to set the exact execution order yourself. You get total control. Step 2 is automatic optimization, where you let an internal mathematical algorithm determine the absolute best arrangement. But be warned, standard undo functions cannot reverse automatic optimization changes. Once you click it, it rearranges the whole structure permanently. Step 3 is relying on implicit dead times, where toggling a specific property inside the editor forces the system to automatically correct the insertion position the very moment you make a new connection. Section 4, Managing Runtime Groups, Organizing the Parts. If organization blocks are the core architecture of our engine, runtime groups are the structural subdivisions nested neatly within them. The overarching task is the organization block. Inside that OB, we nest runtime groups, and then inside those groups, we placed our actual logic blocks. And this isn't just for neatness or organizing your workspace. Runtime groups guarantee that associated channel drivers and technological blocks execute collectively in a shared, predictable sequence. They literally ensure that related parts fire at the exact same time. Sometimes, though, you need to literally turn a specific part of the logic off. And you can suspend execution in 2 different ways here. First, there's static editor control. You go into the properties and manually untick the active box. The editor will literally show a visible strike-through, confirming it's structurally bypassed. But then we have dynamic logic control. This is where you connect a live piece of logic directly to the EN, or enable, parameter. The system displays a question mark in the editor because it honestly doesn't know the status until runtime. And you absolutely must remember this. It's the override rule. Dynamic live data connected to an EN pin will permanently supersede and override any static checkbox setting you made back in the editor. To make all this grouping a whole lot easier, modern chart-based management tightly binds continuous function charts right to dedicated runtime units. So when you create a chart, the system actually automatically generates its own isolated runtime groups specifically for it. These units are assigned permanently and exclusively. It creates complete structural isolation, which means no block from an external chart can ever accidentally wander into this dedicated execution space. Okay, Section 5, Essential Execution Checkpoints, the final inspection. Here is your rapid-fire summary of the 4 core checkpoints required to keep this system running perfectly. First up, valid interconnections. You have to ensure your data properly routes across different charts and invisible IOs. Second, organization block fundamentals. Know exactly which priority level your OB operates on. Third, run sequence control. Verify you have actually eliminated those multi-cycle dead times using manual or algorithmic optimization. And fourth, selective downloading. Make absolutely sure you utilize the architecture of the CPU to transfer only strictly configured changes into the live target system without disrupting everything else. So the crucial point is this. If you take absolutely nothing else away from this explainer, remember the golden rule of the priority pyramid. A higher priority OB will immediately interrupt the processing of any lower priority OB. You could have the most perfect logic in the world, perfectly tuned, but if a higher priority system event occurs, your baseline code stops instantly. Understanding that hierarchy is truly the ultimate key to mastering Pcs7 execution. We have covered a tremendous amount of ground today, looking really deep at exactly how your programmed logic interacts with the live operating system. So I'll leave you with this final thought to ponder.
With all this incredible power and granular control under the hood, how will you optimize your next run sequence to eliminate those multi-cycle dead times and guarantee absolutely flawless execution in your next facility? Thank you so much for joining me on this explainer, and happy engineering!